Okay, so we're going to conduct an analysis of variance to see whether or not, a number of means share equality up to k factors of some categorizing variable, resulting in different means. Are they all equal? Well, in order to do something like this, you have to meet certain requirements. So let's take a look at what those requirements are. First is that the approximation, or the distributions have an approximately normal shape, that they're approximately normal. It's kind of a loose requirement. Just as long as the distribution isn't too far from normal, you should be okay. Another requirement, again, a little bit loose, is that each of these populations has the same variance. Again, not too bad of a requirement. As long as they're not wildly different, you should be okay. Next, we need simple random samples, and our samples have to be independent of one another. So the data you get for one treatment level is independent of the data you get from another treatment level, and they're all categorized in one way. So they're all, from older roller coasters, or all from newer roller coasters, or somewhat recent roller coasters, etc. So categorized only by that one variable. So those are our requirements. And from there, we can test mu1 equals mu2 equals mu3 all the way on up. Now these different levels have lots of different names. They're called treatments, factors, groups. I've heard lots of different ways to refer to those. But let's start out with getting rid of a few problems that you're going to face as you work through this. You can find these handouts on D2L. Here's the first one, example A. And I've already filled in this little box for you. It says a treatment is a characteristic used in an analysis of variance that allows us to distinguish different populations from one another. So it could be the length of a cigarette, could be the size of a car, could be how old your roller coaster is, could be what type of diet plan you used, or what diet and exercise plan you used, etc. So lots of different ways to categorize things into different populations. Now, the first part of this says the accompanying data table contains chest deceleration measurements. And that's going to come from like an insurance company testing out a car with a crash test dummy, and you want to see, how much force they endured in a controlled crash. And they did this for small, mid-size, and large cars. It says, assume that a researcher plans to use a 5% significance level to test a claim that the different size categories have the same mean chest deceleration in the standard crash test. Complete parts A and B below. So just so you can see it, let me share with you what the null hypothesis would be in this case. So this is example A. If the mean deceleration for this is the same for all of these, then that means mu sub small, mu sub mid-size, and mu sub large, they would all be the same. They'd all have the same mean chest deceleration. What's the alternative? The alternative is always kind of the same. At least one of these is different. The above means is different. Okay, great. Let's actually turn our attention to some of the problems that come directly out of your homework. It says, what characteristic of the data suggests to use an ANOVA? And I'm kind of sympathetic to the first one. It says that there are 3 samples of measurements. The second one says The measurements are categorized according to one characteristic of size. Third one, the population means are approximately normal. And then the fourth one says, nothing specifically indicates that analysis of variance should be used. Well, that one's not it. This is a requirement, but it doesn't necessarily indicate that you should use an ANOVA. The correct answer in this case is B. The measurements are categorized to the one characteristic of size. You had small, medium, and large cars. So I'm certainly sympathetic to the first answer. I mean, that's probably a better guide for you as you're taking an exam and trying to decide, well, what test do I want to use? And the reason for that is because all our other tests deal with one or two populations, right? This is the only test that we have that can handle multiple populations. So the fact that there's more than two should pretty much scream out, all right, we're going to do an analysis of variance on this one. That's what it should. The second one says, if the objective is to test the claim that the three size categories have the same mean chest deceleration, why is the method referred to as analysis of variance? That goes back to the distribution involved here and how you set up your analysis of variance table. Basically, you're comparing the variation within the treatment to the variation between the treatments. So if I can find it again here we go. Can I make that bigger? Yeah, maybe a little bit. So what you'll be doing in this case, the case of the top speed of older roller coasters, recent ones, and the newest ones, is you're comparing what's the variation like within each treatment to what it is like between the treatments. So you're analyzing the variability of what's going on here, and that's why it's called an analysis of variance. And so as far as this is concerned, the method is based on estimations of the common population variance. So it's the first answer here, is what I'm saying. All right, so those are just a couple problems you're going to face in the homework on my stat lab. Let's get a little bit more involved with some of this on a more intimate level in terms of working with an analysis of variance table, an ANOVA table. In a test of weight loss programs, 200 subjects were divided such that 40 subjects followed each of 5 diets. Each was weighed a year after starting. After starting the diet, and the results are in the analysis of variance table below. Use a 5% significance level, test the claim that the mean weight loss is the same for the different diets. So, okay. One thing that should be jumping out at you is that we've got essentially 5 different populations that we're going to be comparing. You can't do that with the stuff that we did in Chapter 8, nor Chapter 9, 10, or 11. The only place you can do that is an analysis of variance. So this is example B. Your null hypothesis in this case is going to be that mu1 equals mu2 equals mu3 all the way up to mu5. Your alternative is that at least one of the above measures is different. One of the above means is different. One of the above means is different. Second step is we're going to choose alpha. I'm sure they'll be given to us, so let's take a look back at that. 5% significance level, so we're okay there, 0.05. They already input the data for us, which is how they got the analysis of variance table. What we need out of this is a p-value. I need a p-value from this data set. Well, all right. Does anyone see a p-value for me? Perfect. Right up here. It says it right there, p-value. Now that actually comes from the F distribution that you see here. There's the critical value for the F distribution. That's if you're doing things kind of old school. Old school would mean what you do is you figure out what F distribution you're going to be using, and then you find out, okay, if alpha is going to be 0.05, then this value of F is going to put 5% of the area in the right tail. And the way you work it is if your test statistic lands in here, then you're going to reject H naught. If it doesn't land in there, if it lands somewhere over here, you're going to fail to reject H naught. And then you base your decision on where did your p-value, or where does your F statistic land. Now they actually gave that to us in this particular example. The critical value was 2.418. So 2.418. Our value of F was 4.0759. So if you take a look at it on the scale, our F value falls in the rejection region, which is okay. Nothing wrong with that. This is the classical approach to doing this. Much easier is to use the p-value approach. P-value just says, all right, is p less than alpha? So what do you think? Is p less than alpha? If p is less than alpha, what are we going to decide? Reject. Reject H naught. Beautiful. Done. All right. So, and thank you out there for your answers in the chat. Appreciate those. So the last thing then is to state your conclusion in words. I'm going to move on to a different sheet here. In this particular case, I'm not sure that's really clear what H naught was, but I'm thinking it was, or excuse me, what the original claim was. I think it's H naught. Test to claim that the mean weight loss is the same for all different diets. So, yeah, that puts our original claim in H naught, and we can state in this part that there's enough evidence to reject that original claim. So there is sufficient evidence to reject the claim that each diet results in the same weight loss. Yay. And that's it. There you go. So there's example B. We'll do one more like this, and then we'll kind of get our hands dirty with some actual data. Elena?
Can we use that same wording, the conclusion sheet for this?
Yes.
It works better.
Yeah, I mean, that's essentially what I'm mimicking it off of, is this one. Although, pretty much I think most of the time, your claim that you're going to be testing is in HO. So you'll either not have sufficient evidence to reject it or have enough evidence to reject it. So it's going to be one or the other based on that. So yeah, good question. That sheet, you can still use it. Comes in handy. I guess the big thing that I like about the sheet is that since I started using that wording the conclusion sheet, people stopped saying that there's a probability or we're confident that this happens. I mean, it's a much cleaner wording of the conclusion using that sheet than I got beforehand. So yeah, keep using it. Anything else on that one? All right, well, let's keep going here. So example C. And again, you should be able to find this handout in the content section. This one comes from data that or an analysis done on a TI-83, 84 graphing calculator. You can do this stuff on your graphing calculator. It's just so much more user-friendly to do it on stat disk. So here we go. Samples of pages were randomly selected from 3 different books. And I don't know how to pronounce this. The Fleisch reading score? Fleisch reading score? I don't like the way that sounds, Fleisch reading score. We'll just go with Fleisch, okay? The Fleisch reading scores were obtained from each page. And the TI-84 plus calculator results from analysis of variance are given below. Use a 1% significance level to test the claim that 3 books have the same mean Fleisch reading ease score. All right, so let's see. Now, the thing that I've complained about in terms of the book before is that they strip away anything like remotely interesting about this. But fortunately for us, I actually brought the book today. So let's take kind of a quick look. And the books are The Bear and the Dragon by Tom Clancy, Harry Potter and the Sorcerer's Stone by J.K. Rowling, and War and Peace by Leo Tolstoy. So, all right, at least a little bit more interesting. What would you think? Do they think all 3 of these books have the same readability? I don't know. I'm thinking, I've never read War and Peace. I heard it's quite the big, thick tome of a book. But it strikes me as being pretty deep. And I'm guessing that one, and I have read some Clancy. That's kind of tough sometimes. Well, not tough, but it's not easy. Probably a nice way. So I'd be surprised if they all have the same reading score, but we'll find out. Let's see here. So go back here. Use a 1% significance level to test the claim that all 3 books have the same Fleisch reading ease score. So first things first, I'll start with a null and alternative hypothesis. And for myself, a lot of times I actually like putting something a little bit more descriptive than mu1, mu2, mu3. So I could put mu sub C, meaning mu sub Tom Clancy, mu sub T, meaning mu for Tolstoy, and mu sub R for J.K. Rowling's. That all 3 of these have the same mean ease of reading score. And the alternative is what? Can anyone tell me what the alternative is here?
At least one is different.
Yeah, at least one of the above is different. Nice. And I think they said they use the 1% significance level? All right, so we're good there. Step 3 has already been done for us because they put the data in. But now we need to get to step 4, which is the p-value. And there's something I want to point out to you about the p-value. If you take a look here, I've highlighted that. It's in yellow. Let me see if I can't maybe zoom in a little bit. There you go. So 6.919. And at first glance, you might say, well, wait a minute. Isn't the p-value supposed to be between 0 and 1? Probabilities are always between 0 and 1? And the answer is yes. But there's a little extra something in this if you look at the output. It's 6.919 e negative 4. So what on earth is e and then a minus 4 all about? Anyone know? Yeah, nice. It's in scientific notation. Yeah. So it stands for 6.919 times 10 to the negative 4th. So if you wanted to put a regular decimal notation, where are you going to move the decimal? To the left or to the right by 4 places? Good. To the left. 4 places. So when I do that, I move it 1 place past the 6. I get to move it 3 more places, resulting in 3 zeros and then the 6.919. So probably a little easier to read it there and compare it to alpha up here. But it's up to you. I mean, if you got something like that, just at least know what it is. You will get output like this. Not from Statis. Statis is always just going to give you a nice decimal, which is nice. Because then you don't have to think, right? It's just like, all right, I can look at that one. But here you got to think a little bit. So what's our decision? Maria, what do you think we're going to do here?
Reject.
Yeah, reject H naught. Good job. Reject H naught. Definitely a difference in these. All right. So step 6, going back to this was our original claim again. There is, well, I'll let you take a crack at it. I'll give you a couple seconds. If you want to throw your answer in the chat, that's great. All right, so anyone want to give their version a try? Test it out. Anyone wearing plaid, sitting in the far right of class? Oh, thank you for volunteering.
It said there is insufficient evidence to support the claim that all the books have the same readability.
Okay. Elena, do you agree?
Yeah, I just said like the opposite. I said there is sufficient evidence to reject the claim.
Okay, so one says there's insufficient evidence, one says there's sufficient evidence. Does someone want to cast it? What's that?
She said that there is sufficient evidence to reject the claim.
There's, yeah. But Heather, you said that there was insufficient evidence?
Yeah, to support the claim.
Insufficient evidence to support the claim. All right, so let's take a look here. Which claim is which? Now, I guess the way I see it is that there's, well, let's start out by deciding where the original claim is. I believe it's in HO. So let's take a look back here. These are 1% significant test claim that the 3 books have the same mean reading ease score. So that would put the original claim in H naught. So here's our original claim. And we rejected that claim, right? So there was enough evidence to reject that claim that all three of these books had the same reading ease score. So can you reconcile that with what we got here? Okay. All right. And let me just take a quick look here. The chat. Yeah, well done. Well done. Several of you out there getting it. Awesome. Hey, that's great. Let's try one where we actually get our hands dirty with some data. And hopefully you've opened up that link. It's on D2L. And we're going to look at example D here. The data found below measure the amounts of greenhouse gas emissions from the three types of vehicles expressed as CO2 equivalents. Use a 0.025 significance level to test a claim that the three different types of vehicles have the same mean amount of greenhouse gas emissions. All right, well, let's see. Be nice to know what the three different types of vehicles are. It's probably small, medium, and large. And let's just double check back here. You should be able to open up the data link. Is that working for you guys? All right, this is good. And let's copy this data here. Now you notice that the columns are not all of equal length. That's okay. You don't have to have them the same length for this test. It's not like a matched pairs test from section 9.3. So, all right, let's see, example D. So our null hypothesis is that mu1 equals mu2 equals mu3. Our alternative is that at least one of the above is different. At least one of the above means is different. Okay. Alpha was set as kind of a weird number. Did anyone pick that one up? Yeah, 0.025, which is kind of unusual, but all right, you know, a little variety, spice of life, that's good. 1, 2, 3, we've got our data, and let's input that. So copy it from Google Sheets here. And paste it into StatDisk. So let me clear this all out. And paste it in. And I'm hoping, fingers crossed, that it pastes it in different columns and didn't give you spaces in between. Yay! I don't know why I didn't think of this earlier. It's just, Let's set our significance level to 0.025. So I'll put in a 2 in there, squeeze that in here. Our data are in columns 1, 2, and 3. We're going to make all the necessary assumptions, simple random samples, normal populations, and equal variances. Bam. There we go. Lots of great output here. You can see how an analysis of variance table works. Down here, if you take the sum of squares, 22.52, and divide it by the degrees of freedom, you get the mean square. If you do the same thing with the error, 7.00457, 475 I should say, divided by 24 gives you this really small number over here. And the ratio of these two gives you your F statistic. Now all that's well and good, but what we need is not the F statistic, not the critical F, but the p-value. So the p-value here is a big fat 0. Nothing. So, for my zoomers, what's that tell us to do with H0? There's your p-value. What are we going to do in step 5? Still got a chance to answer if you want to get one in before the time's up. Okay, I guess we got all the answers we're going to get. Yes, a resounding reject H naught. Yeah, that's a really small p-value, like 0. So reject H naught. Let's go back and take a look and see if the data, or excuse me, if the problem tells us what our original claim is. And yes, it does, right here. So test the claim that the different types of vehicles have the same mean amount of greenhouse gas emissions. So that means our original claim is part of which hypothesis? HO or HA? HO, good. So there's your original claim. And our decision was to reject that. So there was sufficient evidence to reject the claim that all 3 of these vehicle types have the same greenhouse gas emissions. There is sufficient evidence to reject the claim that all 3 vehicle types have the same greenhouse gas emissions. Nice. Okay. How'd that one go? I'm going to let you try the next one. So the next one is example D. How about example E? Refer to the accompanying data table which shows the amounts of nicotine in milligrams per cigarettes in king-size cigarettes, 100 millimeter menthol cigarettes, and 100 millimeter non-menthol cigarettes. The king cigarettes are non-filtered while the other 2 are filtered. Use a 5% significance level to test the claim that the 3 categories of cigarettes yield the same mean amount of nicotine. So again, the data should be there for you. Might want to set up the null and alternative hypothesis first. Keep in mind that this is the claim that we're testing, that all 3 categories of cigarettes have the same mean amount of nicotine. So those 3 categories are king size, 100 millimeter menthol, and then 100 millimeter non-menthol. It might be just as easy to do mu1, mu2, mu3. So we'll go with that. Just keep in mind which one is which. Example E. At least one of the above means is different. Okay. So there's step 1, here's step 2. What are we supposed to use for alpha? 0.05. All right, good. 0.05. Step 3 is to put in our data. So let's take care of that. And no, that's the wrong data set. So Let me go back to here. Let's catch all this data here. Copy on that. And then clear out the old stuff. And let's paste. That's looking like the right stuff. Our data's in columns 1, 2, and 3. We can readjust our significance level and then evaluate. All right. Why don't you see if you can't finish it up, at least to the point of deciding whether or not to reject or fail to reject. All right. You guys got a conclusion for me? Alicia? Actually, sorry. Brittany?
Yeah, we reject, and there's sufficient evidence to warrant rejection of the claim that all 3 cigarettes yield the same amount of mean amount of nicotine.
Also, yeah, perfect. The data provides sufficient evidence to reject the claim that all 3 cigarettes have the same amount of nicotine. Perfect. Perfect. And let's see here in the chat. Same conclusions. Good deal. Good deal. All right.
When we do the conclusions, do we say, like, have the same amount of nicotine or the same mean amount?
Probably better to say the same mean amount. I like that better. So in your conclusion, if you want to say it has the same mean amount of nicotine, it's probably better. Yeah, because the individual cigarettes are probably going to vary naturally. So you're looking at the average if you want to be very precise. Yeah. Yeah, great question. Let's take a look at the roller coaster data that we had. We played around with a couple times. And that'd be our last data set. So it's a big one. You have to kind of scroll down quite a ways. And as a reminder, this is the top speed of the roller coasters for older, recent, and newest roller coasters. So for me, I'm going all the way down to 105 on this table to get all the data. Obviously, not each column is the same length. That's okay. Copy that, Control C or Command C, depending on if you have a Mac or a PC. Then let's paste it into here. I think I can just paste right over it. Yeah, that seemed to work. What hypothesis do you think we'll be testing here? What makes sense given our current section? Yeah, one-way analysis of variance. Yeah. So these are all categorized by how old they are. So we have 3 different ones. Let's see, it was recent. Yeah, category 1 is oldest, and then recent, and then newest. Newest being since 2000. So now you can use mu1, mu2, mu3. It's up to you. H0, mu1, mu2, mu3. Personally, I like it when they're subscripted, with something different, like mu sub old, mu sub recent, and mu sub n. I mean, that's kind of nice, but you're not going to see that in the book, nor in Stat Lab, regrettably. That's all right. The alternative is that at least one of the above is different. One of the above means is different. Now, we're kind of making this one up as we go, so we can also choose our value for alpha. What would you think? What's a good value for alpha? All right, yeah, 0.05. 0.05 is a very common one, and there's nothing that critical about this problem that we need to dip down to, say, 0.01. You'd want to go to 0.01 where you really need to be sure of something, that the consequences of a type 1 error are pretty big, that kind of thing. We don't have that worry in this particular case. This is just kind of an academic exercise. Step 3, we input our data. Step 4 is the analysis of variance, and we need to get a p-value. So let's do that. Got my significance level adjusted correctly. Select the proper columns, and then let the computer do the rest. Evaluate. All right. Someone tell me in the chat what I need from this output. Let's take a look here. Yeah, there we go. Rocking on that one. A p-value. P-value is kind of small on this one, 0.00002. All right, bunch of people weighing in on that one. That's good. How about somebody here, Caitlin? What should I do? Accept or reject?
Reject.
Good. Reject H naught. Nice. So reject H naught. Let's assume that our null hypothesis was this one, that all 3 coasters have the same mean. Seems like we're throwing that one out the window. So then what? Well, there is sufficient evidence to reject the claim that all 3 categories, all 3, do I use categories? All 3 ages of roller coasters have the same mean speed. Yay. Nice. Nice. Looking okay on these? Thumbs up. How about my zoomers? You guys doing pretty good on these? Feeling good? All right, excellent. Thanks for the feedback. Let's call it a day on this section. I think we're doing pretty good. So Let me stop things here.